Hello, everyone, and welcome to today's 802 Tech Talk on the development of IEEE 802.3 800 gigabit and 1.6 terabit Ethernet. My name is Jennifer McLean. I'm Senior Manager for Education Products with IEEE Educational Activities, and I'll be helping to moderate today's event. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Please note a few housekeeping items before we get started. At the bottom of your screen are engagement tools that are resizable and movable, so you can move them around to make the most out of your dashboard space. If you have questions for today's panelists, you can submit them through the Q&A widget on your screen, and we'll answer as many questions as time allows. If you click the green resources icon at the bottom of your screen, you'll find more information about IEEE 802 standards and past and future virtual events. Finally, the on-demand link for today's Tech Talk will be emailed to all registrants approximately 2 hours after we finish. And if you'd like to tweet about this event, please use the hashtag IEEELearn. Our panelists today are Paul Mikulich and John D'Ambrosio. Paul is the chair of the IEEE Committee on Standards, overseeing the advancement of technical standards activities across all IEEE societies and councils, and is chair of the IEEE Computer Society's 802 LAN-MAN Standards Committee, overseeing 75 active technical standards and 50 projects under development for wired and wireless networking applications. John D'Ambrosio works for FutureWay Technologies, a U.S. subsidiary of Huawei. He is a member of IEEE 802 Executive Committee and is currently the chair of the IEEE P802.3 200 gigabit, 400 gigabit, 800 gigabit, and 1.6 terabit Ethernet task force. We'd like to welcome everybody, and I will now turn it over to Paul to get us started.
Great. Thank you, Jennifer, and welcome, John, and everyone that's joining us in the audience. Before we get started, though, I'd like to just issue our standard disclaimer. I want to make sure that it's clear that the opinions that John and I share during this Tech Talk are our own and not a position of the IEEE's. So with that, let us get on to what we're going to be talking about today. The role of standards is crucial for many parts of the economy, and the technical standards that 802 develops are crucial for the networking industry. And they enable inventors to bring research through and companies to through the labs into products and into services that we now all use on a regular basis. Right now, we're running this Tech Talk over 802 based networks. And today we're going to be talking about, you see outlined in the blue box, the 802.3 working group, which focuses on the wired interfaces for physical layer and media access control. We're going to be talking about one of the largest projects in that working group, which is being led by John, that's developing interface standards to run at up to 800 gigabits per second or 1.6 terabits per second. And we're going to dive into a little bit of the details regarding that project. So, man, sorry about that. So yeah, we're going to be diving into the details of that. And this slide that I show here shows the overall structure of 802 and how we're organized. Basically, there's wired activities that's in 802.3, and then we have several groups that are developing the wireless interfaces. The most popular is the 802.11 interfaces, which are commonly known as Wi-Fi. So, John, thanks for joining us. I know that you are extremely busy running your project, and we're fortunate to have you join us this morning. And audience, you are also a crucial part of this Tech Talk. Please ask questions that you can do via the Q&A box that's in your On24 display, and John and I will do our best to answer them at the end of the Tech Talk. So let's get started with a brief overview of what we're doing in 802.3, 800 gig, and 1.6 terabits per second. And John, one of the things that 802 is focused on, our mission is to develop high quality, market relevant standards. And maybe the first thing you can address is, how does this project achieve 802's mission? So John, take it away.
Okay, well, thank you very much, Paul, and thank you to everybody for attending today. Let me touch on a real simple idea here, and that is, and you kind of touched on this already, Paul, Ethernet is used everywhere, right? And this is just a simple chart that I'm showing right now, simple diagram, just trying to get that point illustrated. You know, we look at Ethernet and it's in consumer, enterprise, data center, mobile, all over the place. And I'm just showing a few of them here. And there's lots of different products that are used throughout this ecosystem, right? So I think, you know, from my perspective, I typically think of the server, switch, and routers. And all of this has Ethernet connections. A couple of years ago, the 802.3 community, in keeping up with its tradition of monitoring network bandwidth, released its 2020 bandwidth assessment of networking. And what we found was that if you compare the forecasted traffic of 2025 to 2017, what you'll see is that the traffic levels, depending on the applications, are growing anywhere from 2.3 to 55.7 times the traffic levels of 2017. So in order to keep supporting all of these different applications, Ethernet really needs to grow the capacity in these networks. So we're going to be providing in this project a whole slew of new higher speed Ethernet-based solutions that can be used everywhere.
All right, John, as you point out, there's no question for the need of increasing the capacity of the underlying networks that are used globally. I like to call that the plumbing of the internet. Can you give us a sense of the breadth and scope of this project and how it is able to address that growing need for more capacity?
Yeah, absolutely. And I think before I move on, what I'll just say is that when we look at all of these different networks, there is no one size fits all for all these networks. They use a host of different physical mediums, and that's exactly what the former study group that defined the DF project had to take into consideration. So when you look at all of our objectives, you know, first I'll note we have 200, 400, 800, and 1.6 terabit. You'll notice in this other column, I've got assumed signaling rates. So you'll notice that there's, in some cases, we're doing 100 gig. In some cases, we're doing 200 gig. Some cases, we're not sure what we're doing. We might do coherent and do 800 gig. And then all of these different columns define all of the different objectives that this project will be targeting. So the AUI refers to electrical interfaces. This is something that connects, you know, if you think about it, inside of a system box, it connects any chips. We have an AUI that we call chip-to-chip AUIs. And we also have an AUI for connecting from chips to modules. So a lot of Ethernet uses optics. And in some cases, even active assemblies, either copper or optics. And they use these AUIs. But then you've got BP backplane, copper cables, which is a twin-ax solution, different reaches of multi-mode fiber that are parallel, different reaches of single-mode fiber, and then also, you know, we've got these long 10 and 40 kilometer reaches. So we're really covering a large amount of all of the different solutions that are typically used in an Ethernet family.
Excellent, John. So this is a really big project. I look at all those boxes that you have in that table. I find it incredible that you're going to be able to address all of those interfaces. it's one of the largest projects in 802.3. And so roughly how many people are working on this project right now? I know you just got started, but share with us the number of people that you have on your team and, you know, how they plan on splitting up the work.
Okay, well, you know, let me answer your first question about how many people are involved. And I think we need to understand that there's really two levels of involvement. There's, you know, the people who actually attend the meetings, and then there's all the people back at their home offices that are supporting the work, right? So it is a much bigger number when we think about it from a global industry perspective. But just to put it in perspective as to how many people are coming to our calls, mind you, in today's COVID world, everything's being done at this point via teleconference. We regularly have anywhere from 150 to 200 people attending our calls. So it's a very large project. Yeah.
Yeah, it is huge. And one thing that I'd like to note, in your table, you have interfaces that are identified at 200 gig and 100 gig and 400 gig. Can you explain, you know, why are those interfaces necessary when this project is titled 800 gig and 1.6 terabits?
Well, actually, the webinar is called 800 1.6. The project itself actually is 200, 400, 800, 1.6. It really has to do more with how we're going about doing the project, as well as what is the most efficient way for us to address the entire networking. Remember, I said bandwidth is growing everywhere. So originally, the scope of the project was beyond 400 gig. And, you know, we decided on 800 because we recognized during the study group that it was late and we needed to work quickly for 800. And given that, you know, a normal higher speed project usually takes about 5 years, based on input that we got from customer, end user type individuals from end user background, it was clear that 1.6 was not far behind. So we knew we had to do 800 and 1.6. And you'll notice a trend when you start to look at some of this stuff. You'll see, you know, if I look at the 500 meter single mode fiber, there is solutions there that are based on 1 pair of fiber, 2 pair of fiber, 4 pair of fiber, 8 pair of fiber. And that's kind of how we got into this. And what I mean by that is that we recognize to do 800 gig. Initially, we'll be doing 8 fibers in each direction of 100 gig, but in the future, we'll be going to 200 gig signaling, right? So you would need 4 times 200, 800, 4 fibers. Because we already have 8 pair, well, then you can also support 1.6, 800 times, 200 times 8. This gets confusing with the math sometimes. Now, the new higher speed projects are going to be defining this, but the way Ethernet has worked in the past is that we develop new technologies and then we go back and we provide lower cost, higher density solutions for the existing speeds as well. So rather than, you know, wait to start a new project to leverage the technology that's being developed right now, we recognize the whole dichotomy of 1, 2, 4, and 8 pairs, and we basically are going to develop specs for 200 and 400 that are derivatives of the work that we do for 800 and 1.6. So it's really the Ethernet community trying to work faster and smarter to deliver more solutions quickly. Now, you asked how we're going to divide up the work, and I think that's a great question, because when you look at this chart, you get a, you know, when I put this chart together, I'm like, holy crap, you know, this is a lot of work, you know, as we said, you know, one of the biggest projects in .3 history, but it's not really as bad as it seems. You know, what I mean by that is that we can look at this and we can start to divide things up, and we're really going to use a lot of technology reuse. So the first grouping is, you notice there's a number of things related to where there's an assumed signaling rate of 100 gigabit per second. This work is going to leverage work that's either been completed in .3 already or is underway in .3. So in the case of work that's been completed, we've already defined in the 802.3 CU standard work to do, signaling to do 100 gig per fiber for reaches up to 2 kilometers. So we'll be able to use that. And, you know, we have solutions already in standards that support 1 and 4 lanes. We'll just grow that to 8 lanes, okay? In CK, they're doing a lot of electrical work. So they're defining AUIs, backplane solutions, and copper cable solutions, all based on 100 gig. That project was formed when 400 gig was the max. So they have 1, 2, and 4 lane variants. And then we have the 802.3 DB project that is also doing multi-mode fibers for 100 gig. Okay, so we're going to reuse that work. And, you know, if you think about it, there's a table and you add another column to address the number of lanes. And that's really what it comes down to from a spec writing perspective. Now, I said there's logical groupings and there's a second grouping, and that's all the electrical work that we're going to have to define. So solutions for electrical interfaces, the AUIs and the copper cables. I won't be surprised if we decide to add backplane to this in the future once we get into some discussions, because backplane and copper cable are usually very similar. So once again, you see the 200 gig signaling. We're developing that to provide solutions for 800 at 1.6, but we also recognize it's applicable to existing 200 and 400 gig Ethernet. Next grouping then is the optical work. And really we're creating, in this case, an engine to do 200 gigabit per second optical signaling. All right, and this is those 2 columns are all 502 kilometers, and with the exception of this over 4 lambdas, this is all parallel fiber solutions. So it really is the same basic engine that's being used to fill all of those. So there may be some tweaking between 500 meters and 2 kilometers because of the different losses of the fiber, but then it just becomes 1, 2, 4, or 8 lane variants. And then the last grouping, where's my mouse? The last grouping is this 10 and 40 kilometers. We haven't made a decision as to where we're going to go, and I would say that this is probably going to be one of the areas of intense technical debate, right? I mean, and by that I mean where we have some really new decisions to make. I look at a lot of the other work that I've talked about so far as just turning the speed up. I don't anticipate it being anything more than that. We'll have our normal arguments about budgets and, you know, what the exact numbers are, but that's very different than the 10 and 40 kilometers. If you look at most of optics in Ethernet today, they use a direct detect optical technology, but there's also another technology that's used for the telecom space, which is called coherent signaling. And that's more for longer reaches. It's been used a lot by the telecom people for, you know, the reaches that go 80 plus kilometers, hundreds of kilometers. And we're going to look, and there is a possibility that that may be brought down into the 10 and 40 kilometer space, because doing a direct detect signaling at that speed and reach would be extremely challenging. And that's going to be one of the intense debates, I would imagine, in our group.
Right. Yeah, John, this is a great diagram. It contains a lot of information regarding how you split up the work. And I'd like to encourage the audience. I know it's complex, so please feel free to ask questions, and we will address them at the end of the Tech Talk. John, you mentioned that the attachment unit interface, that AUI column, is one of the key interoperability interfaces for the project. Can you give us a little more insight as to why that's the case? Is that the core engine that you were speaking about, or is it something else?
It's something else, actually. So the core engine that I was talking about was the engines to do a given signaling on a given lane, and by lane I mean a differential pair for electrical signaling. On cabling, it's the signaling path essentially. So it could be over a fiber, or it could be a lambda over a fiber. That's what I really meant by the engine. In the AUI, yeah, it is very important. It is one of the key interfaces because it really provides all of the interconnections inside the box. It's, the guts of the box are all connected with Ethernet interfaces. This is what they use.
Okay. All right, so you've got a tremendous amount of flexibility with all these individual interfaces. Let's pick one column in the chart and drill down on the benefits of the 1, 2, 4, 8 pair approach for, let's say, the 500 meter single node fiber column.
Okay, so I'm going to be a little bit more specific and focus in on the 200 gig aspects of that, because that's really where it becomes applicable. But let me make a point here. If you look at the Ethernet technologies up until about this point in time, we were using this parallel approach already. All right, we really started doing this before. I think that's a mistake by some people, where they think that when you talk about an Ethernet that it has to be one signal. That's not the way it is. You can have multiple signals combined to deliver that Ethernet rate. 1000 base T, the most popular PHY in history, most successful PHY in Ethernet history, is over 4 pair. And that approach has been around for a long time. We did this in the 802.3 BA project that defined 40 and 100 gig, where we had 4 lanes of 10 gig. Or 4 lanes of 25 gig to give us that rate. That was basically what people were doing. Now, in the BS project, we grew that to 8 lanes, and as I've pointed out, that's how we're going to be getting to 800 gig in the near future, by doing 8 lanes of 100 gig. So now the industry has changed, and we're no longer doing 1, 2, and 4 lanes. Now we're doing 1, 2, 4, and 8 lanes. And that's, I'd have to say, because going faster on a given lane is getting more and more challenging. So we just are adding lanes to make it happen, and that's how we're dealing with it. But what's happened in the industry is this concept called breakout. So remember, I said we're going to focus in on the 200 gig signaling, and we're going to look at, okay, yep. I have 8 lanes. So imagine you have a port on a box. Don't think of it as an Ethernet port of a single rate. Think of it as a universal port that can support multiple mediums and multiple Ethernet rates. And what you do is you essentially can split up. Remember, we're talking about a lot of parallel media, right? So 8 parallel fibers, okay, in each direction. So you could use those fibers either as the total link, and that's kind of what we're illustrating here. So imagine you have a 1.6 terabit port. You're using all 8 fibers times 200 gig to give you 1.6. You might break that down, and you might want to say, I don't need to use 1.6 capacity at this point. What I really need is a higher density solution for 800 gig. So I can split up those 8 lanes and create 2 Ethernet ports of 4 lanes. So 4 times 200 gives us 800 gig. So now you have 2 ports in that one universal port. Or maybe you decide you want a high-density 400 gig solution or a high-density 200 gig solution. For 400 gig, you would use 2 of these fibers at 200 gig to create a 400 gig port. For 200 gig, you would use 1 of these fibers. So it provides the end user with a lot of flexibility to address multiple Ethernet rates to support different architectures. You could have a very high density, 8 by 200 gig Ethernet port, and that's a really big deal for a lot of like the machine language stuff and all of the AI applications where you really need to have an everywhere to everywhere style connection. So you would see that people are using this today with 1 to 4 ports. We believe, based on the input that we've received, that they'll be using it for all 1, 2, 4, and 8 lane implementations. In addition, it's I know you said use the example for single mode fiber, but this same concept is applicable to the AUIs, our backplane solutions, the copper cables, the multi-mode fiber, and the single-mode fiber. So you will have a very powerful box or very powerful port in whatever box is used in the future.
Great. Thanks, John. That's a great explanation, and it illustrates the flexibility in a tremendous way. So the project just started last month. How is the task force organizing its activities to systematically make progress on such an ambitious program?
So as I pointed out, we got a lot here to cover. And we basically are starting off with a holistic approach in mind, where we're going to look at all of this stuff simultaneously in order to address the needs of the architecture to enable all of those physical layer specifications. We're going to use something called forward error correction, FEC. And you'll hear that term a lot because it essentially does add coding gain, right? So you have limitations on what you can do with channels. There's insertion loss characteristics. This is a way through the coding to get gain to solve the channel, essentially, right? But there's lots of different schemes. You know, if I look at this simple example that I have right here, where I have a MAC talking to the optics through an AUI and then going over optical cabling, you might have, you know, these are just some of the different FEC schemes that are out there. There's what's called an end-to-end scheme, where you would have FEC in the MAC and it goes all the way to the other MAC. You might have segmented, where the FEC gets terminated and then re-FEC'd with a new FEC code somewhere else. You know, you can imagine the MAC, the module, the MAC. Or you might have concatenated, where you have a FEC that's applied at the MAC level and then more FEC is applied at the optics where it's not terminated. So we really need to figure out what architecture and what schemes to support all of these different layers. So that's really our first priority at this point.
Right. Thanks, John. I know I've listened in to some of your meetings, and I know that forward error correction is a major topic. So that brings us to the end of our portion of the Tech Talk. Thanks very much, John. Let's go to some of the questions. So here's one with respect to lanes. Stephen asks, can we expect 8 lanes to be short-lived and to be consolidated to 4 lanes as the technology matures?
Well, that's kind of a tricky question, okay, because it talks about 8 lanes, not 8 lanes per rate. And I think the answer is that 8 lanes per rate will eventually progress for that rate down to 4 lanes. So 8 lanes of 100 to do 800 gig will eventually become 4 lanes of 200 gig. But, you know, people are still going to be wanting to support that 1.6. So I think the 8-lane implementations themselves will continue to exist, and we'll just build on this concept of 1, 2, 4, and 8 lanes, and then apply a new signaling rate, and you get to where you need to be. So from a lane implementation perspective, I think it's here to stay. From a rate perspective, it will progress.
Okay, very good, John. Thanks. Here's a question regarding long reach applications. So with respect to 40-kilometer range, what do you envision would be the power requirements per transmit receive module? Could you maybe also give an estimate on the requirements of the SerDes and repeaters necessary for this type of application? It's a great question. John, can you respond to that?
Yeah, it is a great question. Unfortunately, it's a little premature at this point for me to be able to give you answers. This is an area where we're really starting to talk about coherent signaling. 40 kilometers, you know, if 10 kilometers is difficult to do direct detect, 40 kilometers is only going to be that much more difficult. And the power estimates, I don't really have a good feel for that at this point. That's not something that we've gotten into. I've heard people throw out numbers like 30 watts. not based on the solution, but based on the form factor and asking if it can fit into these form factors. I think this one is a kind of a wait and see for some of the decisions. Now, regarding the requirements of the SerDes and repeaters, I'm not sure if the individual is referring to inside the box, or maybe he's talking about some sort of optical repeater. I'm going to assume he means what's inside the box. And, you know, going back to what we were talking about before, it's going to be the same sort of thing to get to the optics. I suspect that, you know, we'll be talking about for 800 gig, 8 lanes of 100, 4 lanes of 200. And this is one of the things that, you know, just kind of working a little bit here. We have all of these different variations that we need to worry about. This is why the FEC architecture comes into play, right? So I suspect that people will want to do coherent with 8 by 100, and in the future progress it to 4 by 200. I can't go much further into with the repeaters, though. That's still kind of an architectural debate that we're having.
Yeah, yeah. Okay, great, John. We're at the bottom of the hour, but let's take one more question and then we'll wrap up. Question is it feasible to use end-to-end forward error correction when you need to deal with both co-packaged optics as well as pluggable modules? Great question. John?
Yeah, it is a great question. And this is one of the ones that we're having a lot of debate about, okay? And I think the question in itself is kind of incomplete because it doesn't say what co-packaged optics, okay? And what I mean by that is if we're talking 10 or 40 kilometers and we're starting to go coherent, the general rule of thumb, I would say, is that most people are assuming coherent will need a different FEC, okay? In regards to, let's say, the 2 kilometers and below, where we assume it's going to be more direct detect, this is one of the issues that we need to look at. It's a good question. We haven't worked through these type of budgets yet, and we'll need to work through that. I think the question about feasibility, I'm not really concerned about that in terms of being able to do it, but the end-to-end FEC is really the bigger deal. Ideally, people would like to use end-to-end FEC, but whether that's the right approach or not remains to be seen as we solve the channels.
Okay, great. So I'm going to wrap it up now, John, and thanks to the audience and the questioners for their great questions. Here's some additional information that's available at these links. And I would like to encourage everyone that's out there listening. The work that we do in 802 is open and available to everyone. We encourage you to come participate in our activities. You know, some of your questions regarding the forward error correction and the coherent optics are going to be topics of active debate. And in order to participate, you simply need to show up, and you can engage in that discussion and that debate, especially if you bring, you know, specific experience in those topics to the group. So I'd like to welcome anyone that's out there that's not participating in 802.3 DF to please consider participating. And as you know, because of the pandemic, we're 100% online these days, so it's relatively easy to join the discussions. And lastly, just like to let everyone know that Tech Talk series continues with a discussion on single pair Ethernet in March. In April, we're going to be covering wireless specialty networks. That's the work being done by the 802.15 working group. And we'll be diving into coexistence topics in May. And with respect to coexistence below 1 gigahertz, and then for coexistence between 802.11 and 5G networks, that'll be discussed in June. So with that, I'd like to bring it to a close. Jennifer, do you have any closing comments?
Yes, thank you, Paul and John. Just a reminder, the on-demand link for today's event will be emailed to everybody in about 2 hours. As Paul mentioned, the next 802 Tech Talk on single-pair Ethernet will be on March 30th, starting at 9 a.m. Eastern Time, and you can find the link to register for that event in the resource list. And before you leave, if everyone could please complete our feedback survey at the bottom of your screen, we'd really appreciate it. And thank you all very much for your time, and have a great day.
Great. Thanks, Jennifer. Bye, everyone. Thanks, John.
Bye, everyone. Thank you.